So just as a recap, this is brought to you by the Philippine-American Academy for Science and Engineering. PAASE is an international organization of scientists and engineers who have distinguished themselves in scholarly and research activities and who are of Philippine descent, based in the Philippines, the US, and elsewhere. Pangatlong linggo na po ito ng mga PAASE Talk Session. Alam po kasi namin na bilang mga biyahasa sa siyensya at enhinyeriya, nasa atin ang responsibilidad na tumugon sa pangangailangan ng ating mga kababayan gamit ang ating mga kaalaman. So moving on from the land to the sea or the water as we started, we have two more talks more related to the water environment. The upcoming talk is by Dr. Marla and Maniquiz-Redillas. She's from the engineering division in the Civil Engineering Department of De La Salle University. She received her doctorate degree in civil engineering, major in environmental engineering from Hongju National University in South Korea. She has worked for over a decade on water quality, diffuse pollution, stormwater characterization and management in urban, agriculture, industrial, transport-related land issues. She serves as a board member of the International Water Association, Diffuse Pollution and Eutrophication Specialist Group, and the editorial committee member of the Journal of Wetlands Research. So may we now call on Dr. Marla Maniquiz-Redillas for her talk.
Thank you very much for the introduction, Doc Menchi. So here is my presentation. A pleasant morning to each and everyone. I am Marla Maniquiz-Redillas from the Civil Engineering Department at De La Salle University, Manila. As we all know, sustainable agriculture is one of the greatest challenges more than ever. Sustainability implies that agriculture not only secure a sustained food supply, but that its environmental, socio-economic, and human health impacts are recognized and accounted for within national development plans. Today, I am going to talk about water demand and pollution in the agricultural sector and the paradigm shift in agriculture water management, which is what we call NBS or the nature-based solutions. And to be able to understand the application of NBS, I'm going to share with you the research that I did when I was in South Korea on constructed wetlands. And hopefully, we could acknowledge the challenges and the need for NBS in the new normal. Current global water usage is unsustainable and must be reduced in order to secure access to water for the next 100 years. The map on the left highlights the large amounts of water withdrawal, which is water that is taken out from the water system, and consumption, the water that humans can no longer be used by continent and sector. Taking account for differences in population and in the ratio of water consumption to water withdrawal, we can evaluate the efficiencies in water use between nations based on these two characteristics. It is evident that in Asia, the highest withdrawal and consumption could be found. The map on the right shows the overview of the water use based on sectors across the world. The Philippines' water withdrawal is agriculture dominant. This means that any waste also comes in large quantities. Most water is wasted in surface water runoff and evaporation. An incredible competition is observed between water demand in the agricultural and industrial sectors and the recent rise in household demand alongside with a growing number of people in our world. Agriculture accounts for 70% of global freshwater consumption and represents the dominant use of fresh water, and there are severe and increasing freshwater shortages in many areas. Except for water loss through evapotranspiration, agricultural water is recycled back to surface water and/or groundwater by means of runoff. Thus, agriculture is by far the leading cause of water pollution and considered as a major source of degradation of surface and groundwater resources through its discharge of pollutants and sediments to surface and or groundwater, through erosion and net loss of soil, by poor agricultural practices such as improper use of fertilizers, pesticides, herbicides, and insecticides, bacteria from livestock, through salinization and waterlogging of irrigated land, and it is a victim through use of wastewater and polluted surface and groundwater which contaminate crops and transmit disease to consumers and farm workers. According to the Environmental Management Bureau, rapid inventory of point sources reveal that the agricultural sector had the highest contribution, accounting for 45%, while non-point sources that include agricultural runoff contributes to 61% of the total pollution load. In the assessment of nutrient and pollution loading from croplands into the Manila Bay system, the biggest type of nutrient contributed is that of total phosphorus, which could be attributed to the croplands that comprise 46% of the entire watershed, with rice, corn, sugarcane, and coconut as the most extensively cultivated crops. Of the four sub-watersheds, Pampanga River Basin, that cover mostly agricultural areas, provides the greatest amount of pollutants. Agriculture exists within a symbiosis of land and water, and therefore appropriate steps must be taken to ensure that agricultural activities do not adversely affect water quality so that subsequent uses of water for different purposes are not impaired. Just recently, in 2018, during the World Water Day, a new concept was launched in the World Water Development Report that seeks to inform policy and decision makers inside and outside the water community about the potential of nature-based solutions to address contemporary water management challenges across all sectors, and particularly regarding water for agriculture, sustainable cities, disaster risk reduction, and water quality. Nature-based solutions are inspired and supported by nature and used to cost-effectively contribute to the improved management of water. The defining feature is not whether an ecosystem being used is natural, but whether natural processes are being proactively managed to achieve a water-related objective. NBS can mimic natural processes and build on fully operational water-land management concepts that aim to simultaneously improve water availability and quality and raise agricultural productivity. There are many concepts available that either align or can be comparable to the definition and scope of NBS, as you can see on the figure on the right. In principle, NBS aims to contribute to the improved management of water resources at both the micro and macro levels. Moreover, they support a circular economy that advocates greater resource productivity while reducing waste and avoiding pollution through reuse and recycling processes. The inclusive character of the NBS concept has both strengths and weaknesses. There is, for example, no straightforward distinction between NBS and other human-induced management of ecosystem services. Moreover, there is a danger that the wide coverage of ecosystem concepts by NBS creates multiple interests for different stakeholders, whereas only a few goals can be met simultaneously. To address these concerns and to reflect the inherent heterogeneity and complexity of the interaction between NBS and ecosystem services, 3 NBS typologies were suggested, as you can see on the table, that clarify trade-offs between the degree of engineering and the delivery of ecosystem services for the stakeholders involved. These typologies should not be considered as a static representation of possible NBS interventions, but are dynamic benchmarks for many hybrid NBS that exist along the gradients used, enhancing their flexibility and problem-solving capacity. For example, constructed wetlands involve a type 3 intervention that subsequently can be managed as a type 1. Source to sea concepts, for instance, will apply type 2 and type 3 interventions in order to restore natural vegetation and control surface flows for agricultural production. NBS also offer cross-cutting solutions to meet the Sustainable Development Goals, or SDGs. NBS contributes to SDG 15 by protecting the sustainable use of terrestrial ecosystems that provide favorable conditions for water-related ecosystem services that directly underpin poverty alleviation efforts, or SDG 1, the Zero Hunger Initiative, SDG 2, ensure water and sanitation services, SDG 6, and mitigate negative effects under climate change conditions, SDG 13. An interesting Type 3 NBS example is that of constructed wetlands that offer ecosystem services to improve water quality by filtering water, trapping suspended solids by vegetation, and immobilizing pollutants that are either taken up by water vegetation or deposited. Wetlands provide high-level water treatment techniques like deposition, nitrification, and anaerobic digestion of organic wastes and microbial soot. Water treatment mechanisms also hold for the processing of excess nutrients derived from agriculture that are, for example, absorbed by wetland soils, or for organic nitrogen converted by microorganisms into inorganic chemical structures that are taken up by plants. So the first constructed wetland case study is located in Yeonmu, Nonsan City, South Chungcheong Province in Korea. So this constructed wetland has a total area of 19.2 square meter that drains a total catchment area of 11 hectares. This particular wetland is a type of a free water surface flow, and it is designed to receive secondary piggery wastewater effluent treated from livestock wastewater treatment facility during dry days, and stormwater runoff from livestock from the whole catchment area during wet seasons or wet days. There are several vegetations that are planted in the components of the constructed wetlands. As you can see here, this constructed wetland has shown water quality improvement in terms of increasing the dissolved oxygen content from the influent to the effluent, also the reduction in nutrients such as total nitrogen and total phosphorus. The second constructed wetland treat streamwater partly from watershed area of 73% forests and 25% agricultural area with the 2% urban areas from the houses, nearby houses. So this constructed wetland is a type of a meandering, continuous type freewater surface with several components such as sedimentation zone, deep marsh, shallow marsh, and planted with different vegetation such as this. Now, based on our monitoring on these constructed wetlands, the water quality from the inlet to the outlet was greatly improved. This constructed wetland was monitored during non-storm and storm conditions. So it was found out that this constructed wetland greatly reduced the runoff flow rates and flows, thereby reducing the potential risk of flooding in agricultural areas. Historically, water management practices in the agricultural sector were viewed as a driving force behind natural habitat degradation, purposefully obstructing the functioning of ecosystem services These controversies became manifest, for example, in the management of wetlands, rivers, and lakes that, on the one hand, provide ecosystem services by supplying water for agriculture, while on the other hand, the quality of water bodies is affected by high concentrations of agrochemicals. Yet there is a growing understanding that interventions that sustain or improve the state of and quality of ecosystems are also beneficial for agricultural development and agricultural water management. So this lists the challenges and the need for NBS for sustainable agricultural water management in the new normal. It is anticipated that in the new normal and in the next few decades, the agricultural sector will remain the dominant user of water. NBS are potentially a powerful strategy to transform the agricultural sector to be both a beneficiary and custodian of ecosystems. Indeed, NBS adoption provides opportunities to organize the nexus between agriculture, ecosystem, and water to support sustainable food production and reaping the benefits of a well functioning system. I would like to acknowledge our research team in Gongju National University, the Brain Korea 21 Plus LIDGSI research team. So these are some of the members. We have a lot. And for all the supporting agencies for funding our research on constructed wetlands. Well, thank you very much and have a good day. Parang nawala. Nawala yung host. No.
Dr. Menchi is back.
I'm so sorry. Marla, I caught that last one. I was just going to ask you one question. I know water is not really top in the discussion of agriculture right now. It's more production, it's more trade, maybe, as they've been listing. How do we raise the profile of water? How do you think we should be raising the profile of water in these discussions? Water use.
Yeah, as far as I know, in the agriculture sector, well, I am working in environmental engineering field, so water is the most important in the environmental engineering field. So I guess for the agricultural sector, so since it was mentioned in my presentation that agriculture is the sector with the highest water demand among all of other sectors, it means that in the future we will be needing more water. And if we don't have enough water in the future because of we don't take care of our water quality, then we don't have enough water for our agriculture as well. And that is not the only problem, because agriculture will be in competition with other sectors like industries and domestic use or the residential uses. So there will be conflicts in water. So yeah, I guess it is really hard actually to consider or to focus the attention on water. But I believe that if we will start at this point, I think in later on, because it is really hard to actually persuade the government or other agencies in with respect to environment, kasi that's the parang least priority talaga. Pero yun nga, so we have to really start early, because in the long term we will reap all of the benefits if we are going to focus on this nature-based solutions. So that's my comment.
I think Yeah. We should get more of you into the discussion of the biologists. That's why you're here in this forum right now.